Welcome back to another fun-filled episode of AP Physics C Review. So today I want to look at the field and potential for a ring of charge. So if we have ourselves just a normal ring, and we want to look at what is the electric field and potential at this point, then, we'll say the ring has some charge Q and some radius R, etc., etc. Standard stuff. So R, and we'll say plus Q. I always like plus is better because the arrows point away. I can just draw it like a line. So once again, we're going to look at an individual charge element. So let's look at this one first here. And I say, what's the effect this is going to have over here? So this is going to help me figure things out. So let's say we're a distance, I don't know, X away from there. And we're obviously distance R upwards. So my hypotenuse here, we'll call it little r. I want to find field and potential, the electric field and potential. So the question that I first want to ask is, what will be easier to find, field or potential? And will one help me with the other? Well, we've done a lot of field so far. Let's try potential first. Now, to remind you guys that electric potential is a scalar. So let's write that down real quick. And what that means to us, that kind of became one word, oh well, is that it doesn't have vector components. So I can just add it normal. Adds like a regular number. So I can say, what's the electric potential from this point? And so then if we say this point here has a charge of dq, then dv is equal to 1 over 4 pi epsilon naught times dq over r, which is the formula for the potential of a point charge. Well, if it's for a potential of a point charge, it's going to be v and q, right? But here we're doing dv and dq. So now if I say, what's the potential as I go around my circle and add up all of the potentials, then I don't have to consider the angle, right? I can just go around and add it all up. So if I can say, so when we integrate this, I want to say integral dv is equal to 1 over 4 pi epsilon naught integral dq over r. So I need to replace this dq with something that has a spatial dimension, right? So normally we do lambda dx, right? So that's a very common thing we do in these situations. But now we're going about a ring. So I can't really do lambda dx because I need my variable to be r, first of all. And when I go around, my r isn't what's changing, right? I need to include an r. I don't want my variable to be r because my r isn't what's changing. What's changing is my angle theta. And when I'm basically integrating around my circumference. So I can't do this one. Instead, what if I do dq is equal to the differential of the circumference? So that's going to be in terms of theta, in terms of angle. So that's normally circumference we could write, as circumference is 2 pi r. So what if I say, dc should equal then, and I want my theta to be my variable, theta times r. But in this case, we're going to use capital R because we have a fixed radius. And I've already called the little r something else. So then this really needs to be not theta, but d theta, right? So I'm going to say this is going to be r d theta there. So that's going to be an integration variable this time. And then, of course, our bounds for our integration are going to be from 0 to 2 pi because we're integrating around a circle. Now that I know that. Or I guess when I'm doing q, this should technically be q on this one because I'm integrating over q still. So when I change this here, I'm going to say v equals 1 over 4 pi epsilon naught integrated from 0 to 2 pi of r d theta over r, right? So now, are we done here? Can I just call it good? And do it? So what the question I have to ask myself, is there any theta dependence in this r or that r? And looking back at our picture, I mean, this r is a constant, so there shouldn't be any theta dependence. And this r should be the same for any angle we pick, because all equidistant at that point, they're all a distance r away from the axis, so it should be fine. So I think what we can do now is we can just factor those guys out. So I can say 1 over 4 pi epsilon naught times r over r, integral from 0 to 2 pi d theta. So if you guys want to skip forward till the end of this, go ahead. Well, the section. So then just 2 pi, right? So it's going to be 1 over 2 epsilon naught. Oh, I forgot my lambda. So let's put our lambda back in. Lambda. Oop, I don't need two of those. Lambda. So this is going to be lambda r over r. And if I want to write this in terms of my other variables with this, in terms of this x here, right, it was probably going to be important. We can go ahead and replace this r with the square root of x squared plus capital R squared. So then it's going to have lambda r over 2 epsilon naught square root of x squared plus capital R squared. All right. Yeah, I think that's pretty good. But you might be looking at this and saying to yourself, I don't like this because my units of R cancel, or meters cancel, so I end up with charge over epsilon naught. But that's actually not correct. So since this isn't infinite, it'd be nice to put it back in terms of Q, right? So what is lambda? So lambda is, well, one way of thinking about it is, lambda is charge per meter, right? So I like to remember that, right, Q is circumference times lambda. So if I want to solve for lambda, that tells me that it is Q over 2 pi r. So that 2 pi I brought out earlier, and cancel on the bottom, I'm actually going to put it back. So V, putting that in, is going to be 1 over 4 pi epsilon naught, because the two 2's become a 4, and that r on top is going to go away, so I'm going to get Q over r. Well, and then I can simplify, go back to this, put it in this term here. So I can say 1 over 4 pi epsilon naught times Q, my mistake, over x squared plus r squared. All right. So that's how you're going to find the potential. So once you find the potential, oh, you can't see that last line, I'm sorry. Once you find the potential, can you use it to get the electric field? Yeah, you can. You can also find the electric field straight away by integrating around the ring and then multiplying by a cosine theta term. So if we called, this angle theta here, you would want to multiply by the cosine theta term to get just the x component. But in this case, actually, I'm sorry, that we shouldn't call that theta. We should call it the other one. We'll have to, I think theta would be easier to go over there. Yeah, you can do either way. I think it's fine, because you can still say, well, this you put it in terms of your hypotenuse and x and y variables, so you're good either way. Yeah, and you're just taking the cosine, so it's fine. So, and that angle is going to be constant, so maybe we should have called that phi, I guess. Let's call it phi. All right, I digress. So yeah, you could find the electric field that way. But what if we do it this way? Well, how do you find electric field from potential? Well, if you guys remember that we can say that electric field equals minus dV dx, right? Or if you want to be real fancy and know some calculus 3, minus grad V, so the gradient of V. But that's if you're real fancy. So I want my integration variable here is x, so I want to just take the derivative with respect to x. So the only thing that matters is taking the derivative of this bottom term. So we can just take a quick derivative and say that this is equal to, we're going to have to bring in x out, right? I mean, maybe I'll just do it real quick and just write it down to make this video shorter. So we're going to get, when we do this, 1 over 4 pi epsilon naught times, well, let's put the q here, pull my x out, and then this is going to be x squared plus r squared, but this is going to be to the 3/2. And if you guys need help on that derivative, you guys can ask me during office hours. But otherwise, I'm going to call that good here. So let's circle my answers, or box them. I guess this is the better one over here, because it's in terms of what was given in the problem. We defined this little r ourselves. And let's go ahead and box this one too. All right. And that's all for today. Well, at least this video. You guys are kind of probably watching at your own pace. Hope you enjoyed it. If you did, hit that like and subscribe button, and hit that bell button for notifications every time we update. I'll see you guys later.